Hello. Today I will present on the topic, Batteries in Space Applications for the course, Battery Fabrication and Testing. Batteries are essential for nearly all space missions. The demand for higher performance is growing rapidly. By 2030, the global space battery market is expected to exceed $5 billion. So let us examine the key challenges first. Standard liquid electrolytes can outgas or even boil, leading to cell failure. Ionizing radiation damages the electrolyte and the solid electrolyte interface, causing capacity fade. In low Earth orbit, temperatures cycle between 40 degrees Celsius and plus 80 degrees Celsius. On the Moon, it drops to 180 degrees Celsius at night. Low Earth orbit satellites experience over 5,000 charge-discharge cycles per year. Cells must survive up to 10 g of acceleration. Traditional Li-ion batteries struggle with all of these. Before discussing new trends, let me briefly summarize what is currently used. Most space missions today rely on NMC, nickel manganese cobalt, or NCA, nickel cobalt aluminium, chemistries. These offer good energy density, around 150 to 250 watt-hours per kilogram. However, they have serious limitations. Dendrite formation can cause internal short circuits. Liquid electrolytes freeze below 20 degrees Celsius without special additives. Outgassing in vacuum leads to pressure buildup and leakage. And cobalt is expensive and has supply chain risks. This is why space agencies are actively researching next-generation batteries. Now, trend number 1, solid state. Solid-state batteries replace the liquid electrolyte with a solid ceramic, polymer, or sulfide material. The main challenge today is manufacturing scalability and interface resistance between the solid electrolyte and electrodes. The second major trend is moving beyond traditional graphite anodes. Lithium metal anodes offer a theoretical energy density of over 500 watt-hours per kilogram, nearly double today's best Li-ion cells. However, lithium metal suffers from dendrite growth during charging, which can pierce the separator. Solid-state electrolytes actually help solve this problem, which is why lithium metal plus solid-state is a very active research area. Silicon anodes are another path. Silicon can store 10 times more lithium than graphite. The challenge is that silicon expands by 300% during charging, causing mechanical failure. New nanostructured silicon designs and composite electrodes are making this viable. For space applications, the high energy density is extremely attractive for deep space missions where every kilogram matters. Even with solid-state batteries still maturing, conventional Li-ion electrolytes are being dramatically improved. For example, the European Space Agency has tested cells that retain 90% capacity after 500 Gray of ionizing radiation, enough for a 15-year geostationary mission. This trend extends the life of existing battery formats without changing manufacturing lines. The fourth trend is not in the chemistry but in the intelligence around the battery. Modern space-grade battery management systems now incorporate machine learning models that run on onboard processors. These models predict state of charge with better than 1% accuracy, even under dynamic loads. State of health, predicting remaining useful life years in advance. Fault detection, identifying a failing cell before it causes a mission failure. Some systems can auto-reconfigure the battery pack, isolating a bad cell and balancing the rest. NASA's latest BMS for CubeSats uses neural networks that were trained on Earth and then continue learning in orbit. This is a major step toward autonomous spacecraft. Thank you for your attention.